All right, welcome to The Explainer. Today, we're going to talk about a piece of equipment in the oil and gas world that you've probably never heard of, but it plays an absolutely vital role in keeping things safe and accurate. We're talking about the surge tank. So let me ask you a question. Picture this. You've got a stream of crude oil coming up at high pressure, and it's all mixed up with volatile, sometimes even toxic gases. How in the world do you measure that oil accurately without, causing a huge disaster? It sounds almost impossible, right? Well, that is the exact problem we are going to solve today. And here's the solution: the surge tank. Now, the simplest way to think about it is as a high-tech, high-pressure measuring cup. But we are definitely not talking about something you'd find in your kitchen. This is a pressurized vessel, okay? It's rated for at least 15 pounds per square inch above atmospheric pressure. And if there's even a whisper of a chance of encountering nasty hydrogen sulfide gas, that's H2S, then using one of these isn't just a good idea, it's absolutely mandatory.
Okay, so what exactly is this high-tech measuring cup doing out there? Well, during well testing operations, it has three incredibly critical jobs. These are the pillars of why this thing even exists.
First off, it's there to verify liquid flow rate measurements. It's like the ultimate fact checker for how much oil is actually coming out of the well. Second, it validates the oil flow meters themselves, making sure all the fancy electronic gauges are telling the truth. And third, and this one is really cool, it's used to calculate what are called shrinkage factors. Think about it like a can of soda. When you open it, it fizzes and the total volume goes down a little, right? Same idea here. This tank measures how much the oil's volume shrinks once all that dissolved gas escapes. Getting this right is the difference between a rough guess and a multi-million-dollar certainty.
So, before a surge tank can do any of that amazing stuff, you have to get it on site and set it up with some serious precision. This whole process is called the rig up.
The tank usually shows up lying on its side. It has to be so carefully lifted into a vertical position because one wrong move could damage the whole thing. And where you put it is crucial. Offshore, it has to be in what's called a Zone 2 classified area. Just think of that as a designated safety zone where the risk of an explosive atmosphere is pretty low, but it's not zero. Finally, you get it all hooked up to compressed air, fresh water, and most importantly, its gas vent gets connected to the flare line. Now, even before the tank leaves the yard, this pre-job checklist has to be done. The crew makes sure it is 100% empty, so you get a clean start for your measurements. They check every single valve to make sure they're operating smoothly, because losing control of the flow is just not an option. And they run a special calculation called an Archi test. This is basically physics homework that predicts how much force the fluid is going to have, and it helps them decide if they need a flow restrictor. And trust me, we're going to see why that is so important in just a little bit. All right, the tank is set up, it's been checked out, it's time for the main event. But hold on, this isn't as simple as just turning on a tap. There's a huge safety step that has to happen first. Before a single drop of oil enters that tank, the operators have to prove that the gas vent line can safely handle all the gas that's about to bubble out of that liquid. Because if it can't, the pressure inside that vessel could build up. And that is a situation you want to avoid at all costs. Next up is something called conditioning the tank. See, an unconditioned tank might have some water left in it from being cleaned. If you just go and dump oil on top of that water, the boundary where the two liquids meet will completely fool the sensors and give you a garbage reading. So to prevent that, the operators first add a little bit of the actual fluid they're about to measure. This makes sure that every measurement from that point forward is pure, accurate, reliable data. Now, let's talk about one of the biggest dangers in this whole operation, something called gas blow-by. This is what happens when the equipment feeding the tank has a problem, and instead of liquid, it sends a sudden, super high-velocity slug of pure gas straight into the surge tank. It's a violent event. And this is exactly why that Archi test calculation we mentioned earlier was so important. To protect the tank from that gas blow-by, you install an adjustable choke, basically a flow restrictor, right before the tank. This thing acts like a gatekeeper. It keeps a constant back pressure on the line, and it prevents that dangerous rush of gas from ever slamming into the tank. You know, we've touched on safety, but let's be real. When you're dealing with pressurized, flammable stuff, safety isn't just a feature, it's everything. Surge tanks are basically wrapped in multiple redundant layers of protection. Let's start at that vent line where all the flammable gas is coming out. It is fitted with a special detonation-type flame arrestor. Now, Its job is simple, but absolutely critical. If, for some reason, something were to ignite the gas outside the tank, this device is designed to stop that flame dead in its tracks. It prevents it from traveling back into the tank and causing a complete catastrophe.
So what if that vent line is hooked up to a flare system? Well, you add yet another layer of safety. It's called nitrogen blanketing. You know how fire needs oxygen to burn, right? Well, with this system, the empty space at the top of the tank is filled with inert nitrogen gas. By pumping in nitrogen, you push out all the oxygen. No oxygen, no fire. It's impossible for anything to combust inside the tank. It's pretty brilliant.
The safety rules actually change a little bit depending on where that gas is going. So if you're venting to a hot flare, you absolutely need that nitrogen blanket and the flame arrestor, no exceptions. But if you're cold venting straight to the atmosphere, which, by the way, is only allowed if there's no toxic H2S gas, you still need a windsock so you can actually see which way that invisible, flammable gas cloud is drifting. And the protection just keeps going. This tank is shielded from every angle. You've got relief valves that protect it from too much pressure. Then you have breaker valves that stop it from collapsing on itself if a vacuum forms. And finally, the entire unit is electrically grounded to prevent even a tiny single spark from static electricity, which could be catastrophic. So the measurements are done, the data is collected, the well test is a success. What happens now? Well, the job isn't truly over until the tank is safely taken apart and decommissioned. First things first, every last drop of that produced fluid is drained out. Then, the whole system gets a meticulous cleaning. The water lines are drained, the sight glasses get scrubbed clean, and the entire tank is flushed out with special water or brine that has corrosion inhibitors in it. It's a really thorough process that makes sure the tank is safe to transport and ready to go for the next critical job. 5. What is so important about the number 5? It's 5 years. That's the mandatory time between what's called a major recertification. And this isn't just a quick checkup. We're talking a deep, deep inspection, visual checks, ultrasonic testing to measure the exact thickness of the steel walls, and a full-on hydrostatic pressure test to guarantee that vessel is strong enough for another 5 years of safe operation. You know, when you stop and think about it, this whole thing, this incredibly intricate system of procedures and safety devices, is all designed to protect just one single vessel. It kind of makes you wonder, doesn't it? What other invisible, complex engineering is quietly working behind the scenes every single day just to keep our world running?